Hello, and welcome to this section called vector operations. It's part one of different vector operations. Now that you know what vectors are, we can talk a little bit about how to use them. And we're going to look today, first of all, at different coordinate systems, and then we're also going to look at how we can determine resultant magnitude and direction, not graphically. So we're going to look at the Pythagorean Theorem and tangent function to help us solve problems so that we don't have to laboriously draw all of these out. So let's get started. So far, we have been looking at motion in one dimension, one-dimensional motion, just one direction. Either we've been looking at horizontal motion, here's just some examples, or vertical motion, either up or down. And we've been using these conventions, the y-axis and the x-axis, to kind of help us keep that straight. We are going to try and combine these now. So when our motion isn't purely horizontal or purely vertical, something different, we need to look at a way to represent that. Let's just give an example here of, say, a car that's traveling at 26 meters per second northeast. This is obviously a velocity vector. It gives direction and magnitude. We can represent that in some different ways. One way would be to use the XY axis and show the car at here we would show the XY axis. We could show our car traveling at a 45-degree angle to the X and Y axes. We could also decide to simply show the car moving along the Y axis and just position that Y axis pointing to the northeast. So what is the correct way, and how do you go about choosing a coordinate system? Well, there isn't one correct way. Basically, the answer to that question would be choose the one that makes the most sense and makes it the easiest to solve the problem that you're doing. It really doesn't matter what you choose. Just be consistent in your problems and make sure that whatever way you do choose, you are consistent with that and refer to that model throughout your entire problem that you're working on. So really, it's up to you, and choose the one that makes it the most simple to solve the problem. So let's look now at how we can use a coordinate system to find our resultant magnitude and direction. We have been using the graphical method. We've been graphing the different vectors and representing them on a graph, literally. Drawbacks, obviously, it's very time-consuming. If you haven't complained yet, I'm surprised. It's also limited in its accuracy. The accuracy is based upon how accurate you are at drawing and drawing those vectors and measuring the angles and the lengths. So a much more simple method of doing this would be a method where we are going to use the Pythagorean Theorem and what we're calling the tangent function. And some of you are familiar with these and some of you may not be, but let's look into that and see how we go about finding our magnitude and direction in ways other than graphing them. Okay, let's start by remembering what the Pythagorean Theorem is. Now, nobody gets scared. You've done this before. It's really easy. This can now become a useful tool for you in physics. But let's review what this was all about when we studied the Pythagorean Theorem. Remember, when we talk about a right triangle, it only can be applied if it is a right triangle, where we have a 90-degree angle in our triangle. And in that case, if we have a 90-degree triangle, then we can use our Pythagorean Theorem, where the length of the hypotenuse squared, the hypotenuse, remember, is the side of the triangle that is directly across from the right angle. That's the hypotenuse. So when we have the hypotenuse squared, the length of it, it will equal the length of one leg squared plus the length of the other leg squared. And these legs are the ones that are that form the right triangle. So our formula would be c squared equals a squared plus b squared. It can be applied to any right triangle and only a right triangle. So therefore, it could also be applied to find the magnitude of a resultant displacement. Remember, when we are looking at displacement, we're looking at magnitude and direction. If we have two displacements that we are adding together, delta x in this case, if we're using the xy plane, and delta y, we can use that Pythagorean theorem idea, if these are at right angles to one another, to find the resultant displacement. This is the resultant, and it happens to be displacement in our example here. So we can say that the displacement squared is equal to the change in x squared plus the change in y squared. So now let's try an example. Using that idea, a camper leaves base camp and hikes 11 kilometers north and then 11 kilometers east. What is the magnitude of the camper's displacement? Well, we can write out our little vectors here. We have 11 kilometers going north plus an 11 kilometers going east. And just writing that out so that you can get in your mind what's going on, we want to find the displacement here. And we're not going to worry about direction yet. We're just going to look at magnitude right now because the Pythagorean theorem will help us determine the magnitude and the magnitude alone, only. So c squared equals a squared plus b squared. Our c squared is our resultant. Our r squared is going to equal 11 squared plus 11 squared. These are the two legs that form the right angle. So we have 11 squared plus 11 squared gives us r squared. When I do the math, 242 gives me r squared. And when I take the square root of both sides, I get 15.6, should say kilometers, is my resultant magnitude for the displacement. So how can we find, now we know how to find the magnitude, that's pretty easy. How do we find the direction of the resultant? Okay, now don't be scared about this. If you have trouble with math, this is really a very simple idea. And if we use the tangent function for right triangles, we can solve very easily for the direction that our vector will take. Let's kind of look at this example here from before. If we have two vectors like this that are forming a right triangle, the tangent function, the definition of that is simply the tangent of an angle. And let's say we want to know this angle. This would be the angle of our resultant vector from horizontal. So this would be a nice angle to know. If this is our resultant vector, we would like to know at what angle is that resultant vector moving away from the horizontal line, from the x-axis. So this would be a nice angle to find. If we'd like to find the measurement of that angle, we can do that because we know that the tangent of an angle, if we're talking about a right triangle, is going to be equal to the opposite leg, which is across from that angle, it's the opposite, divided by the adjacent leg. Here's the opposite to the theta. Here's the leg that is adjacent to that angle. It's the one that, in this case, is forming the right triangle, not the hypotenuse. Hypotenuse is the segment that is opposite the right angle. So if we abbreviate that, tangent of theta equals opposite over adjacent. And since this rule can be applied to any right triangle, it can also be applied to find the direction of a resultant displacement. And I simply replace some of the vocabulary here with our terminology for vectors. We know then if we have these two vectors, we would like to find our resultant vector here, which is going to tell us our displacement. And in order to do that, I'm going to take the tangent of theta and set that equal to delta y for the y-axis, divided by the delta x for the x-axis. Now, in order to solve that, right here, if you knew delta x and delta y, you could solve for that tangent theta by simply rearranging algebraically. You can take the inverse tangent of the left side, could say inverse tangent here, and take the inverse tangent of the right side. Oops. Doesn't look very nice, but when I do that, if I take the inverse tangent of both sides, I end up with simply theta on the left. I got rid of that tangent. And on the right side, I'm going to do the inverse tangent. Another way to write that would just simply be tangent to the -1. It's the same as inverse tangent of the delta x over delta y of that whole term. So that is how we can find the direction of a resultant displacement. Let's practice some of this now. Okay, you're probably wondering why I put a picture of the pyramids on the beginning of this little video, and it's because we have a little pyramid problem. So let's do this together. We're going to use the Pythagorean theorem and tangent function that we just learned about to find the resultant magnitude and direction for this problem. So here's our little example problem. Say a tourist climbs a pyramid in Egypt, right up the side. If that pyramid height is 136 meters and the pyramid width is 2.30 times 10 to the second meters, what is the magnitude and direction of the tourist's displacement while climbing from the bottom of the pyramid to the top? So if that tourist climbs from here to the top, we know the two different vectors that are contributing to that tourist's displacement. The first vector we want to know would be delta x. If I look at my pyramid here I have the height of the pyramid. If the width is along here, I would like to know just this much. In the problem, I am told that the width of the pyramid is 2.30 times 10 to the second. That means this entire length would be that. I only want half of that because that is the only portion that I'm considering, is just this portion right here of that width, which is half. So 1/2 of 2.30 times 10 to the second happens to be 115 meters. So I went ahead and wrote that over there. I know delta x is 115 meters. I know my delta y is just this height right here. And I'm told in the problem that its height is 136 meters. So I wrote that right here. The delta y is 136 meters. So I know this term and I know this term. So those are the things I know. Just wrote those for us again right here. The things I don't know the displacement and the magnitude of the displacement, and I also don't know theta. I don't know that angle. So those are my unknowns. Now, another thing I did to help us solve this problem is that I drew a diagram. I drew several diagrams here. I just drew the pyramid diagram to help you understand why I divided the width by 2. But it's important to write out my xy coordinate system, and I'm placing my starting point at the origin because it makes it really easy for me. I can get my delta y and my delta x really easy if I have my tourist starting point at the origin. And therefore, I'm just looking to find the magnitude of the displacement and then also theta here. So drawing the coordinate system out and drawing a little diagram on there is another important step in solving this problem. So the second step in solving this problem, I have my knowns, I have my unknowns, I have my diagram and my coordinate system. The second step here is choosing my equations. So I've chosen my equations. We're going to use the Pythagorean theorem and the tangent function. And for my Pythagorean theorem, simply instead of saying c² = a² + b², I can say d², That's the hypotenuse right there, and that's what I want to find, too. I want to find d. So d squared equals delta x squared plus delta y squared. So that is what I'm going to do for the Pythagorean theorem, and here is the definition for my tangent function. So the next step is now to plug values into those equations and solve. So when I plug values into my Pythagorean theorem, I get d squared equals the 115 meters squared plus 136 meters squared. I can go ahead and punch those numbers into my calculator. I'm going to need to then take the square root of both sides after I do that. If I take the square root of both sides, I end up getting d equals 178 meters. And since I took the square root, my meters make sense because the units were meters squared under that before I square rooted it. Now I get 178 meters for my displacement magnitude right there. Now let's plug values in for my tangent function to find out what theta is and determine the direction for my vector. So here, tangent of theta is going to equal 136 meters divided by 115 meters, corresponding to the delta y and the delta x. Now, when I punch this into the calculator, again, it depends on the type of calculator you have, so I want to make sure you definitely practice this, but we're going to take the inverse tangent of each side. And when we take the inverse tangent, or tangent to the -1, we simply get theta on the left side, and the inverse tangent of our division problem is 49.8 degrees. So theta will be 49.8 degrees, and the magnitude of our vector will be 178 meters. One other important thing to remember is to make sure your calculator is in degrees and not radians, because that will definitely affect your answer. Also, just keep in mind that we need to remember to make sure we check our sig figs. We have 3 sig figs here. We're limited by 3 sig figs in our problem. Calculators do not figure out significant figures for you. So in the end, check your answer against the number of sig figs that you're able to have by what the problem had in it. So good luck, and if you want some advanced ideas, hold on just a minute. Try solving some of the practice problems using different trigonometric functions. For example, sine of theta would be delta y over the displacement resultant vector. So try some other trigonometric functions and check your answers that way and see if you're getting the same answers, because you should. So look forward to seeing you in class.